lecture, we're talking about observability and the Kalman decomposition. Observability is a property, structural property, similar to controllability, but it's like the dual property. That is, so the question of controllability was, can we, by applying control, drive the system from one state to another state? The question of observability is, by looking at the output of the system for a finite amount of time, can we determine what the initial condition must have been? So suppose we don't know what the initial condition is. Can we, by looking at the output, knowing, for example, what control signal is being applied, can we find the initial condition? So in this case, y of t is going to be given by this. So in the discrete time with no input and unknown initial condition, well, so in discrete time we have this, y of t is given by this expression. In the continuous time, y of t is given by this expression. And so if we have zero initial condition and we apply an input u in some admissible set, then we get the output y. Why not? So the question is there another initial condition other than 0 such that with the same u applied we get the same response? That's another way of looking at this question of observability. So if we collect n, capital N samples, then we look at the output values, and so we see here are the output values. Y0 is equal to Cx of 0, Y1 is equal to Cax of 0, and so forth. So here we're assuming we have that our output is our matrix D matrix is 0, in which case this is what we get. And so we're also assuming that it's unforced. The system is unforced. So we get these sample values. And so notice that each of these values, because it's the unforced system, we don't have a control signal, they're all dependent upon the initial condition. I can factor that initial condition out and I get this matrix. So that's the observability matrix, or the output matrix from 0 to n. And so the question is, so here I have a linear algebra equation. Why are these values known? These values are known. X0 is unknown, and then this is known. And so under what condition does this have a solution? Okay, a unique solution. So notice that in general, this is going to be a tall matrix. And so under what condition? Well, we need to think in terms of null, the null space. So if the null space is trivial, only the trivial null space, then we will have unique solutions. So the equation here will have a unique solution if and only if the output matrix from 0 to n is 1 to 1. So we saw that in the controllability problem, our control map needed to be onto. Now our control map our output map needs to be 1 to 1. In this case, there exists a left inverse L. So if a matrix is 1 to 1, then it has a left inverse, such that when I multiply by the left inverse, I get the identity matrix. In this case, we can solve for x0 as that left inverse times y. So suppose now that there's a non-zero vector in the null space of that output matrix, output map. Then the solution of this equation, for any solution, x0 to this equation, the initial condition x0 can be modified by v. So now I have this term multiplying by the output map, distributing, I get this and this. This quantity is y, this is 0, and so I get y. And so both x at 0 and x at 0 plus v are solutions of the linear equation. So we do not have unique solutions. So our output map then, given by this, is dual to the control map. Instead of b, a squared b all the way up, we have c, ca, and so forth. And so it's going down instead of across. As with the control map, there's a mapping of the spaces associated with this. Remember, with the control map, we were concerned with the range of the control map. In the case of the output map, we're actually concerned now with the kernel or the null space of that output map. And again, we have this nesting that takes place. So K, N, and L. N is between K and L. So the kernel of K contains the kernel of K plus 1. So as we increase K, the kernel decreases in general, in dimension, all the way until we get up to N, in which case the kernel no longer increases as we increase that index. So even though L is greater than N, the kernels are the same. So the kernels of these nest, they become smaller and smaller, and eventually they become as small as possible. Okay, so remember, if, for example, the output map, if K is equal to 1, we only get C. And C in general is fat, and so it has a non-trivial kernel. Okay, it will have a non-trivial kernel. If I add C times A, now I'm making the matrix a little taller, so it's not quite so rectangular. So it's getting closer to square. Then this will generally have a smaller kernel because there are more rows. It has to, the vector has to be orthogonal to. Okay, and so that's why we have this kind of thing. So we have this nesting property of the output map. There are, in the same way that we had tests for controllability, we have tests for observability. And so here we're going to have a number of tests. Actually, we have more tests here for observability. Some of these could actually be given in terms of, could have been written in terms of controllability. We could have had comparable ones, but it's not necessary. So the first thing is AC is observable. So if we notice that the observability is a property associated only with the A and the C matrix, not the B. Okay, the controllability was concerned with the A and the B. The observability is with the A and the C. So for any eigenvector, now this is a right eigenvector. So AV is equal to lambda V. Lambda is a complex value. We have C times V is non-zero. So remember, we had in the controllability, we had left eigenvectors, and we had to have that left eigenvector times B being not zero for any eigenvector. Okay, so we have the comparable thing here. Here we also have the PHR test. Here we have XO instead of XC. So XO is of this form. And this says the matrix XO has only a trivial null space for all Z. Again, we only need to check the eigenvalues of A in this test. Here we have the observability matrix as opposed to observability map that goes up to n minus 1. And so the next test says that the observability matrix has rank n. So another test is that the null space of the observability matrix is only the zero element. That is, it's a trivial null space. So here's a new, so this is comparable to the controllability that said that the range of the controllability matrix was all of Rn. So this one shows the duality more between controllability and observability. So this says that AC is observable if A transpose C transpose is controllable. So we have the same kinds of tests. So notice we have the transposes here working with this. In the same way that we defined uncontrollable modes, that is, we had an XC, and the values of XC for which this dropped rank. In the same way, we have the same kind of thing. Any mode that makes this drop rank, have rank less than n, then any Z that does that is an unobservable mode. And so what this says is there are no unobservable modes. We can also define a Gramian, the Gramian M, which is of this form, that this is positive definite for all t greater than or equal to n. Okay, so we have a Gramian here, just like we did in the controllability problem. Number 9, for any nth order polynomial alpha O of Z, there exists an L such that A minus LC has the characteristic polynomial alpha O. So this is like the state feedback problem, only this is not state feedback, this is actually an observer problem. And we'll come back and look at this when we look at observers. Number 10, a block triangularizing transformation. If we have a block triangularizing transformation, then this guy cannot be 0. Okay, so those are the various tests, and I'm not going to go through and prove them. Basically, they're comparable to what we had for the controllability, and so we're going to just press on. Now, the observability Gramian, the limiting Gramian, that is, if our system is stable in discrete time, then this infinite summation exists, that is, it converges, and this P satisfies this discrete time Lyapunov equation. In continuous time, if our system is Hurwitz, if the matrix A has all of its eigenvalues strictly in the left half plane, then this integral converges, and this P satisfies this Lyapunov equation. So we have the Gramians, the observability Gramian for the system in discrete time and in continuous time. So for the Ackermans formula to apply to this system, if we have a single output system and alpha naught is an nth order monic polynomial, then we can find L to make A minus LC have this characteristic polynomial using this formula. Notice that for a single output system, QO is a square matrix, and because if it's observable, then we have the inverse existing, and so we can compute L from this equation. Now, the observable subspace, this is the set of vectors that can be uniquely resolved in our entire state space. In general, this is not that easy to find. Okay, what's easier to find is the unobservable subspace. Okay, so the complement of that. So the unobservable subspace is where our output map times x is equal to 0. So we can thus indirectly find the observable subspace as all of Rn with this subspace removed. So that's what this means. It's actually, we can think of it as the orthogonal complement of O bar. So that's the observable. So we don't actually say it's the orthogonal complement because it's not necessarily orthogonal. Well, I guess it kind of is, but anyway. So in the same way that we had the controllable canonical form, and our transformation matrix was the controllability matrix, here if we let the transformation matrix be the observability matrix, then we get the system in this form. So again, we get a companion matrix, and then our C becomes this. So this is an introduction to observability. A lot of parallels to what we saw in controllability. In fact, the two properties are dual. They're related to each other. So we're going to move on next to the Kalman decomposition.